My topic, as you can see, is the not so simple pendulum. I will cover mostly some stuff about pendulum, some of the things you already know, some of the things I don't think you have learned about yet. But the really interesting stuff, that will be on my last slide. That is stuff that you can learn further about the pendulum, simply because it would take me at least 6 or 7 lectures to cover the whole stuff. So I'm not going to talk about the whole thing. Just to begin, first, a brief history about the pendulum itself. As you all know, a pendulum is an object which is suspended from a point and is free to move under gravity. And one of the earliest recorded pendulums, well, this one doesn't really look like a pendulum to you, right? But the pendulum is actually inside this. This is one of the very earliest seismometers that was devised by a Chinese scientist, Zhang Heng. And the motion of the pendulum inside this contraption allowed people to figure out exactly where the epicenter, or at least roughly figure out where the epicenter of an earthquake was. And Zhang Heng actually made some of the finest readings of earthquakes that we have from the ancient world. This is 1st century AD. Well, the person whom you all associate with the pendulum is Galileo Galilei, who studied the pendulum and specially talked about the isochronicity, the fact that the pendulum time period does not depend on how it's moving. He studied it over a long, long period, which started around 1602. And the story goes that what it did was actually observe a pendulum hanging from the ceiling in the Leaning Tower of Pisa. And the way in which he figured out that it was isochronous, that all that oscillations took the same amount of time, was by comparing it with the only other source of timekeeping that he had, which was his own pulse. So he sort of measured off the swings of the pendulum against his pulse. In this case, of course, it was not really meant to be a pendulum, it was a chandelier hanging from the ceiling. But effectively, because it swung freely, you could treat that as a pendulum. And he enunciated this law that the time period of a pendulum does not depend on the amplitude, which, as we will see, of course, and as you all know, is not exactly accurate, but it's pretty close to being accurate. Now, continuing with the history a bit more, in 1656, Dutch scientist Christian Huygens, who is famous for many other things, including one of the first wave theories of light, built the very first pendulum clock. And his clock actually, well, it was a huge advance because it was accurate to within 20 seconds in a day, which is compared to the previous timekeeping devices that we have, whose accuracy was only about 15 minutes a day. So you'd be lucky if you could get to within plus minus 15 minutes earlier. The pendulum clock, things became much better. It was around a few seconds now. And now the person who actually played a huge role here was Robert Hooke. Robert Hooke's name, of course, comes in connection with oscillation simply because Hooke's law, after all, is the basic law for the simple harmonic oscillator. But one of the first studies of the conical pendulum, pendulums beyond things which swung just in a plane, was done by Robert Hooke. And it's of historical importance for several reasons. One of them being the fact that by studying the motion of the conical pendulum, what Hooke managed to do was he sort of understood, at least at a conceptual level, what kind of forces would really drive planets around the sun. In fact, it is said that Hooke was the person who first suggested the inverse square law to Isaac Newton. Now, this is a matter of controversy and debate because Newton, not being a very nice person, flatly denied any credit to Hooke in his whole work, and there was a huge amount of acrimony between these two people at that time. Of course, Newton did a lot more than just propose that there's an inverse square law. He went on to figure out what kind of mathematics would actually describe the laws of motion of planets around the sun. He also figured out a lot more, like explanation for the tides and so on. But whether Hooke was the person behind the inverse square law or not has been under considerable debate over the years. But basically, Hooke's ideas came from the conical pendulum. So the pendulum is really important in this whole story. And in 1673, Huygens published a book which I am going to try to pronounce, the name of which, Horologium Oscillatorium Sive Motu Pendulorum. Now, horologium means timepiece. Oscillatorium, of course, a timepiece which oscillates. Sive or Sive is or, demoto is motion. So, this is a book on the motion of pendulums or equivalent theory about. This was a book's title page here. I just skipped through that. And then, of course, is Huygens himself. And in this, he describes something called the tautochrone. This is one of the topics that I'm not going to touch today. But this is basically where he first figured out that Galileo was not really correct when he said that a pendulum is isochronous. But he managed to describe how you would get an isochronous behavior. What kind of curve is it that a particle should move under gravity so that you will really get a time period which is independent of the amplitude. And he also figured out a way of mechanically forcing a pendulum to move along such a path. It didn't turn out to be a very practical thing in the end because what he needed was some solid pieces around which the pendulum wire would wrap. But the wrapping gave rise to a lot of friction. So it didn't really give Huygens what he wanted. But theoretically, this is a perfectly nice thing to do. And it gives you a very nice introduction to the, to various kinds of motion, constrained motion beyond just the simple ones that we study. Now, in 1851, again, another topic which is going to be in my last slide, something which I'm not going to cover, Leo Foucault showed that the plane of the oscillation of pendulum tends to stay the same irrespective of what happens to the pivot. And that essentially means that when the earth turns around under the pendulum, the plane of the pendulum maintains its position. The earth turns away. So when you are on the earth and you look at the pendulum, you see that the pendulum's plane turned. And that was the first direct experimental observation of the fact that the earth really rotates. Of course, we knew that the earth rotates. At least we had lots of observational indications that the earth actually rotates. But this was the first time you could really prove it using a physical device. Now, the final point here is once the clock, this clock, which of course you might call a pendulum clock because you see a pendulum. Well, you all know these are not really pendulum clocks. The pendulum here is for show. These are really quartz clocks. And quartz clocks are so much more accurate than the pendulum clock. And nowadays, we no longer use the pendulum for timekeeping. So, around 1927, the discovery of the quartz clock sent the pendulum clock into oblivion, more or less. You can find some pendulum clocks in mostly in museums or very old houses. But nowadays, they are no longer used for timekeeping. But I would like to convince you, at least show you some stuff which goes towards that despite this fact that the pendulum is really not used for timekeeping any longer nowadays, as a physics device is really very, very important. And it can help you learn a lot of physics, which is rather surprisingly advanced. So first, 4 slides on how to derive the pendulum equation. I'm going to skip through this very, very rapidly because I'm pretty sure this is old stuff to all of you. 4 slides because there are 4 different ways. The first one is the approximate version where you just assume that because you have small oscillations, at least if you have small oscillations, the motion of the pendulum is nearly horizontal. So although the pendulum actually moves in an arc, you can sort of ignore the arciness and think of it as moving horizontally. And there, the horizontal acceleration, of course, is given by the second derivative of x, the coordinate, and ay, that's the approximation. Ax equal to x double dot is not an approximation, but Ay is approximately 0. That is really moving in a horizontal path and not really arcing. That's an approximation. Now, how do you get the horizontal acceleration? Of course, you need a force for that. And since gravity is vertical, it of course does not give you a horizontal component. The horizontal component comes from t. And that's, it's easy to see, it's really t sine theta, that's the horizontal component, or minus t sine theta, being on the opposite direction. And sine theta from this diagram is easy to see is x by L. So minus sine, so this is an exact relationship, by the way. But the approximation comes from the fact that Ay is approximately 0, which means t, the vertical component, which is of course t cos theta. For small oscillations, that's nearly t, and that's equal to mg. So that's the approximation. And once you put that in, you end up with mx double dot, the force in the horizontal direction, equals minus tx by L, and t replaced by mg gives you this. And then you finally end up with the very familiar equation, x double dot is approximately minus g by L into x. And g by L is this quantity which you call omega square, the omega being the angular frequency of the pendulum or oscillation in this case. So if anybody has any questions at any stage, I'm pretty sure nobody has questions about this, but if anybody has any questions at any stage, please stop me then. And if I'm speaking too fast, which I tend to do, also tell me that. Okay. Now, a more exact derivation, I'm calling this more exact and not exact because there are several things, several physical issues that we ignore in all these derivations. Like we ignore the fact that a point of suspension may move. We ignore the fact that there is air resistance. We ignore the fact that the wire has a mass. So that should, it's really not just a point mass at the end of a light wire. All of these, of course, can be taken into account and you can improve upon the approximation stage by stage, but we are going to stick to this approximate thing. And here, again, a very elementary derivation. Here we consider the angular acceleration instead of the acceleration. And of course, for an angular acceleration, what you need is a torque given by moment of inertia times the angular acceleration. And moment of inertia here is ml square, because it's just a point mass m, a distance L from the point of suspension. Now, so the point of suspension is where you are taking, I think I've lost, really, but yeah, I've nearly lost the pointer. Do you have a mechanical pointer? Okay, anyway, I think I can handle this. Yeah. No, okay, this is fine. This is the point of suspension. This is the bob. The tension is directed towards that. And that means that the tension will provide no torque about the point of suspension. It's pointing right at it. The only torque comes from the gravity force, mg. And that's given by minus mg L sine theta. Okay? That's easy. L sine theta is just a displacement or perpendicular displacement from the point of suspension to this. So this length. And this gives us an exact, or at least quote unquote exact result. Exact meaning assuming that you can ignore air resistance, motion of the point of suspension, blah blah blah. You get ml square theta double dot, that's I theta double dot, equals the torque minus mgl sine theta. And therefore you get the more accurate expression for the pendulum. Theta double dot is minus g by L sine theta, and g by L, as you have seen, is omega square. That is the angular frequency of the oscillation. So theta double dot is minus omega square sine theta. This is a more exact derivation. Okay, one more version of this derivation. Okay, by the way, before we go there, we had x double dot equal to minus omega square x, and you all know how that comes about. We assume theta is small, sine theta is approximate to theta. In fact, we are going to talk about how good this approximation is in a while, but therefore, theta double dot is minus omega square theta. That's the approximation. Okay, somebody trying to log in? Okay. Now, the second version of the more exact derivation, let's go through this very, very quickly. This uses energy conservation. Kinetic energy is half mv square v is L theta dot. Potential energy, assuming that the point of suspension is where your zero potential energy is given by minus mgl cosine theta. So conservation energy gives you this equation. Of course, we are assuming no dissipation. And since E is a constant, if you differentiate this with respect to theta, you immediately get ml square times theta dot d theta dot d theta plus mgl sine theta equals 0. And the next step is simply realizing that theta dot d theta is nothing but t2 theta dt. That's v dv dx is the same as d2x dt2. That's something which you are all familiar with. Simple application of chain rule, and that once again gives us the same relation. Okay. So finally, a more sophisticated sounding derivation, but essentially the same thing. You start with a Lagrangian, which is in this case kinetic energy minus potential energy. Kinetic energy and potential energy we worked out the other time in the previous slide, so you know what they are, and you simply calculate the requisite derivatives, use the Euler-Lagrange equation, and you get the same equation all over again. So any one of these derivations, at least any one of derivations, the last three derivations would do, because they would all give you theta double dot plus omega square sine theta equals 0. Okay. Now, we are going to take a break from the pendulum for a while and go on to talk about the harmonic oscillator, for the simple reason that, as you all know, for small theta, sine theta is approximately theta, and you get theta double dot plus omega square theta equals 0. Or this is the approximate equation that's obeyed by a pendulum for small oscillations. In fact, if you have a mass attached to a wall by a spring, and that's where Hooke's law comes in, minus kx is the Hooke's law force, you again get the same kind of equation. The only difference is theta is replaced by x. And here omega, of course, is given by square root of k by n and not root over L by g. Root over g by n. Okay, so now, not only this, these two, many other systems obey this kind of equation. And okay, this is a result which I'm pretty sure many of you have already come across. Almost all small oscillations are simple harmonic. Okay. There is a stress on the word almost. We are going to come to that in a bit. But at least in a conservative system, if you have small oscillations about an equilibrium position, 99.99% of the time it's going to be simple harmonic. You may have been taught that 100% of the time it will be simple harmonic, but there is a small catch there. Okay, and this is a quick summary of, I'm not even going to read this out. You all know what this is, right? This is basically the standard result for the simple harmonic oscillator. And the final result tells you that given the initial conditions, you can find out x of t explicitly in terms of cosines and sines. Now, why is it true that almost all systems give you simple harmonic behavior for small oscillations? The answer is, first of all, it has to be a conservative system. If it then is described by a potential energy. I wrote potential, it really should be potential energy here. And as you all know, if you have a okay, that's a very bad spelling error, but anyway, apart from that, the statement is right. If you have a point of stable equilibrium, u of x should be a minimum, which means, of course, that you expect this to be whole. That first derivative should vanish, and the second derivative should be positive. And that means that if you are very close to x0, you're talking about small oscillations about the equilibrium position, can use a Taylor series and expand Vx in powers of x minus x0. So this is a generic Taylor series statement, but here note that V prime, this term is 0, this term is positive. Now Vx0 may be very large, but Vx0 is a constant, so it does not have any implication as far as the dynamics is concerned. The first term, which is dynamically important, is this term. And for small oscillations, these terms are going to be, for sufficiently small oscillations, these terms, the higher order terms, are going to be too small. So you can neglect all the higher order terms. You couldn't possibly neglect v prime x0, x minus x0, but it's exactly 0. So you drop it anyway, because you are at equilibrium. And now, from this you immediately get force, which is minus dv dx. I'm doing this in one dimension. You can generalize this to 3 dimensions pretty easily. It's a bit more notational problem, but otherwise straightforward. And it turns out that the force essentially is proportional to the displacement is restoring. It has a minus sign, minus v double prime x0 times x minus x0. So v double prime x0 plays the role of the spring constant in the Hooke's law counterpart. So the important thing is, if a particle is oscillating by a small amount from a stable equilibrium position, the second derivative of the potential at that point, which is positive, behaves like a spring constant. And the equation of motion will essentially be m d2x d2 is minus v, approximately at least this expression, which is essentially the same as the expression for an oscillator. The only difference is instead of x equal to 0, you're oscillating about x equal to x0. So you have x minus x0 as your variable to worry about. And this immediately tells you that this will be oscillating at a frequency of angular frequency given by the second derivative by m, square root of that. And therefore the time period will be 2 pi by omega, 2 pi square into square root of m by v double prime. And for the pendulum, just to verify that we have got it right, v of theta is given by, okay, I dropped the m. There should be an mgl cos theta. Okay, that's v of theta. And therefore, theta 0 equals 0. That is where the equilibrium position is. Cos theta is, of course, maximum, and therefore the potential is minimum at theta equal to 0. And the second derivative of theta 0 is gl. Actually, it's mgl. I've once again dropped the m. Or somehow I thought maybe I was doing this for unit mass or whatever. The only important thing is instead of the m in this formula, because you're talking of angular acceleration here, you should be using the moment of inertia. So instead of m, you should be using ml square. And instead of v double prime square 0, of course, you should use mgl. And then plug that in, you get your very familiar formula, t equal to pi root over L by g. Okay. So this is the derivation, at least for the pendulum, of the time period formula that we have. Now, what we need to do is talk about the pendulum, well, beyond the small amplitude approximation, so beyond the harmonic oscillator. And what we are going to also do is, before we go to talk about that, let's talk about going beyond the harmonic oscillator in general. Simple harmonic oscillations are isochronous, right? They're the same time period irrespective of the amplitude or the energy of the particle. And almost all small oscillations about point of stable equilibrium are too, because they're all essentially simple harmonic. And where Galileo had assumed that a simple pendulum is isochronous, this turns out to be an approximation because sine theta is, of course, not exactly equal to theta. And let's take a look at conservative potential and motion under that in general. Again, something which you all know. If you have a particle moving in a potential energy curve given by this red curve here, and this minimum point is where the equilibrium is, that's where x0 is, and suppose the particle has an energy E, then you all know that the motion will be confined, classically at least, between these 2 points, the so-called turning points of the motion. And A and B here are the turning points, and they're characterized by V of A and V of B are both equal to the energy. So at A and B, the particle has no kinetic energy. The potential energy is all it has. So the particle is momentarily at rest at A and B, and they turn around from those points. That's why they're called turning points. Now, if I want to find out the time period of oscillation, again, I think all of you know this, right? How to find the time period of oscillation for an arbitrary potential? Yes? Do you? Yes or no? That will save me some time. I can just keep on to the next step. Okay, let me just quickly go around this anyway, but this is pretty straightforward. All you do is start from conservation of energy. Mx dot square plus V of x equals E. Rewrite that to give you x dot as a function of x. So this gives you dx dt equal to this expression. Actually, you could have got this or minus this depending on which way the particle is moving, right? The particle could be moving either this way or that way. Depending on which way is it moving, you are going to get either a plus sign or a minus sign. I'm assuming that it's moving from the left to the right for the time being. So I have a plus sign. So dx and dt are related by this simple relationship. And I know that if you start here at time 0 at A, by the time you get to B, you would have gone through exactly half a time period, right? And therefore, you integrate that expression from 0 to t by 2. And of course, for x, you're going from A to B. And this, after a bit of manipulation, just gives you this form for the time period. If you know v of x as a function, you can try to carry out this integral and it will give you the time period. Straightforward. Okay. So just let's see an application of this. Okay, how many of you know the results for this? If you have power law potential, one power law you obviously know, which is 2. That's the harmonic oscillator. So if v of x is given by alpha x square, you definitely know what the time period is going to be. In particular, you know how the time period depends on the amplitude. It doesn't, right? But suppose I did this for n equals 4. I would like you to guess. If you know it already, fine. But if you don't know it, it's a nice thing to try to guess this. If n is 4, how do you think the time period depends on the amplitude? So if the potential is alpha x to the 4 rather than alpha x square, will the time period stay the same with amplitude, go up with amplitude, go down with amplitude?
Go down.
Why? Why?
Because if the amplitude is increased, then the drop will move faster.
Good point. Actually, you're right. The point really is, okay, it's a bit more complicated than that, but basically the idea is right. If the force is much larger for larger amplitudes here, if n is 4, the force is bigger than for the harmonic oscillator. So where the particle is at rest, that is at the end points, the force is much larger, so it speeds up a lot more. And by the time the particle gets close to the equilibrium position where the force is nearly 0, it has already acquired a much larger speed. So it's actually going to go around with much larger speeds on the average when the amplitude is larger. Now, to see this, all you do is note that here, because the potential is symmetric, the turning points will be at equal distance about the center at plus or minus a, where a is given by this expression. Whatever the energy is, E has to be alpha a to the n. That's where the potential energy equals the kinetic energy, and this is where, sorry, equals the total energy. And this is, of course, where the particle turns around. And so our integral, the formula that we wrote down, simply is this. And because this integrand is even in x, I can simply write it this way. The details are unimportant, really. The factors are not that important. What is important is this integral is pretty easy to calculate for n equals 2. It's a very standard, well-known integral. But even if you cannot calculate the integral itself, if you are interested in how the time depends on the amplitude, that is how t depends on a, you can figure that out simply by doing a very simple substitution. Just use x equals capital A times I. That's it. Because if you do that, you are going to get a to the n by 2 coming out from the denominator. You'll get an a in the numerator. Dx becomes a d psi. And now you can take the a out of this completely. More importantly, the limits which involved a before now has become independent of a. So this particular integral actually is a well-known standard integral. It can be written down in terms of gamma functions. But even if you don't know anything about that, doesn't matter. It's some fixed value, right? It doesn't depend on a at all. So basically, what you have found out.
Just 1 minute.
Yeah.
Xi at 1 is going to go up, right?
Yeah. So this integral actually is not xi is not going to blow up, but the integrand blows up at one end. But this integral is finite. This is standard gamma function integral. Here, for example, if you had n equals 2, this is basically sine inverse, and that gives you pi by 2. Okay. So our interest is in how time period depends on amplitude. That's a to the 1 minus n by 2. Okay. So, of course, if n is 2, this is exactly to the 0, isochronous thing. For a cube, where you actually mod x whole to the 3, actually. Mod x to the 3 and not x cube. An x cube potential will not have two turning points, right? An x cube potential goes up to minus infinity on the negative side, so it will not be able to confine a particle. We are talking about mod x cube as a potential. The time period goes as 1 over root a, and for n equals 4, the question that I asked, time period is actually inversely proportional to a. Can anybody tell me what kind of potential will produce a time period which goes as 1 over square root of E, where E is the energy? No, think about it. Root E, well, for a free particle, root E is proportional to what? For a free particle, what is root E proportional to? Momentum, good. Shows that you have been studying quantum mechanics a bit too much. I would have said velocity, I guess. Momentum is fine. But since we are talking about motion, velocity is perhaps more useful to talk about. And you will get 1 by root E behavior for a free particle in a box. That's a bit easy to see, right? The time period would just be the time it takes for it to bounce from one wall to another. Same distance, constant speed, proportional to root E. Okay. Now, the reason why I'm saying this is the following. Very soon we are going to ask a question, which is, can we invert this calculation? Can we go from the time period as a function of energy and talk about, if I know the time period as a function of energy, can I figure out what the potential is? Okay. And the answer turns out to be a bit non-unique. In fact, there are two very well-known and very complicated looking potentials. One is called the Morse potential, the other is the Poincare-Lindstedt potential, both of which actually has this 1 by root E behavior for the time period. Just the same behavior as a particle in a box. Now I'm going to not prove that for you. I'm just giving this as a teaser, because what I'm going to describe next will help you also to figure that out if you wanted to. So but before I go there, there's one very important question, which is, if A is small oscillations should be harmonic, right? So the time, at least for any small oscillation, what you should have, if you were to say, if you were to plot the time period against the amplitude of oscillation, what you really expect is, at least for small oscillations, it should be flat. Then it can change. But for small oscillations, it should really be flat. But that doesn't happen for these potentials, right? 1 by A. The smaller you make A, the larger the time period becomes. And in fact, it tends to blow up to infinity if A becomes very small. Okay. So how do you explain the statement that you have all learned? The small oscillations are simple harmonic and hence isochronous with this result. That here, no matter how small you make A, you don't get toward to isochronicity at all. You get further and further away from it, if anything. So I gave you a proof, right, a while ago, that all small oscillations are orthogonal. That is, all small oscillations are simple harmonic, hence orthogonal. But this result directly contradicts that. Here, the smaller you make A, the worse it becomes, the larger the time period becomes. So, and that happens not only for n equals 4, it happens for any n larger than 2. So, yes, pretty straightforward actually. Well, when we did the derivation, what we did was we started the Taylor series. What did we do? We said V prime is 0, so we will drop it. Okay. And V double prime is positive, non-zero. So that's the first non-trivial term. That's the term I will keep. And for potentials of this kind, where n is more than 2, V double prime actually happens to be exactly 0. So it cannot stop at the second order in the Taylor series, because that's not your contributing term, or that's not your non-trivial term. The non-trivial terms are higher powers. So that's the almost all small oscillations are simple harmonic. Okay. Clear? Okay, the inverse problem. Okay, I'm How long do I really get?
7:15.
Okay, so I think I should be able to manage. But okay, the inverse problem is this. Oops, okay, I forgot that this is yeah. Given the time period of oscillations of a particle as a function of its energy, so if t is given as a function of E, can we reconstruct the potential function V of x? Okay, it turns out that we can, to an extent, not exactly, but to a large extent, we can actually solve this problem. So what we need to do, what we are trying to do is figure out V of x, right? This blue curve here. Our input is T of E. Suppose somebody has measured time for different time periods for different energies and given it to us. Now, it's actually easier to find the inverse function x of V. But there's a big problem with that. Can anybody point out what that is? What is a very huge problem trying to find out x of V? Exactly. There is no x of V, right? For any given V, at least for this graph, you can see there are two x's. So it's not a bijective function as she says, and therefore the inverse function doesn't really exist here. Okay. But what you can do is break this up, at least if you assume that there's only one minimum, which we are going to assume is at x equal to 0. If you're somewhere else, I would just shift my x. Okay. So I'm going to assume that there's only one minimum at x equal to 0, and that will actually tell us that we can describe x in terms of two functions, one on the left, the other on the right. So you can have two functions, x1 of v and x2 of v. These are well-defined functions, at least assuming that there's only one minimum, it doesn't go up and down any further. Okay? Now, what is our time period? This is our formula that we derived a while ago. And if you just forgotten, it's just distance divided by velocity. This root over e minus b is essentially velocity. The factor root 2m is what makes it exactly the velocity. Okay. And you integrate this from x1 of e, which is the turning point on the left. Remember, on the left, x is given by x of x1 of v. So at the turning point, v is exactly equal to the energy. So x1 of e to x2 of e. Okay. Now, whenever you want to do an integral like this, where x has two different versions on two sides, you'll have to split up the range of integration. In fact, you'll have to do it from x1 of e to 0, that is from here to here, where the function is really x1, right? And this should really be v of x1 in the denominator. And from 0 to x2. Again, 0 to x2 of e. And this is dx2, and this should really be v of x2. Okay. And then the next step would be to try to rewrite this in terms of v. That is, change variables from x2. How do you change variables? Simple. For example, this dx1 will have to be replaced by dx1 dv times dv. The vx simply becomes v, because that's your variable now. What about the limits? x1 of e becomes x1 of e is a limit for x1, right? But when x1 is equal to x1 of e, the potential v is exactly equal to e, right? So this will be from e. Upper limit, again, we have assumed that v of x is 0 at its minimum. That's again just a shift. So just a change of variables. Substitution, nothing else. But you have to do two different substitutions on the two halves because x has two different functional forms. But notice that these two integrals are almost identical, right? What is the difference? Well, one is dx1 dv and this is dx2 dv. The other one is the energy. The limits are wrong in one. So you can simply add them up into a single integral, right? So this is q of e as a function where x2 and x1 are given. Now what we are going to do is, okay, this is a clever and not very easy to understand step without knowing some advanced mathematics, but the step is pretty straightforward. The motivation of where the step comes from may be a bit difficult to understand at this stage, but let's see, it works. What we are going to do is multiply q of e. Okay, let's go back to this. What we are going to do is we are going to multiply q of e by a function of e, namely 1 by square root of v minus e, and integrate over e from 0 to some number, of course, with dimensions of energy, say alpha. And we are going to, of course, do it on both sides. Okay. Now we on the right hand side we are doing a double integral. A v integral is being done first. This red thing is actually our t of e, and then we are going to integrate this multiplied by root over alpha minus e and integrate. Right now, what we are indicating here is exactly what this in double integral means geometrically. You are integrating over v first, then you are integrating over e. And when you are integrating over v, you are going from 0 to e. So what you are doing is, for a fixed value of e, say this one, you are going from 0 to v equal to e, that is this 45-degree line here. There's a bit of a stretching in this in the projection. So this really should be a 45-degree line, but it's looking a bit more flat. But anyway, so that strip, integral over this strip is actually the integral in red here. And then, of course, you're integrating over e, which means you're moving this blue strip all the way from e equals 0 to e equals alpha, and you're tracing out an integral over this triangle. Now, the reason why we have to be careful about this particular region of integration is that what we are going to do next is, well, the obvious thing. We are going to do it in the other order. Instead of integrating first over v and then over e, we are going to integrate first over e and then over v. The reason being, if you integrate first over e, note that this unknown thing does not depend on e, right? So it stays outside that integral. It's an integral over v alone. The integral over e becomes something which is very straightforward and standard. Okay, but the limits, when you go this way, e goes from v to alpha, right? You're going integrating over e first. That means you're holding v fixed, so you're going horizontal. So e goes from v to alpha, and v of course goes from 0 all the way up to alpha. So this is what the integral becomes. Now, this inner integral, the integral over e, should actually be very familiar, or at least would have been familiar a few years ago when you were in your higher secondary, because this is a very standard problem which you have to solve over and over again. One of those clever problems which people solve in higher secondary over and over again. The value of this integral, straightforward, is actually equal to pi. That is one of those standard integrals which people solve. But then, if you take that pi out, end up with this, and you're done. Because notice, you're integrating the derivative of x2 minus x1 with respect to v. And that means you're going to get x2v minus x1. So note that the solution to the inverse problem is the following. T of e is given. You divide by that by square root of v minus e. I've just changed alpha to v in the last stage. That's it. Nothing else has been done. And you would have got x2 alpha minus x1 alpha. Now we have x2v minus x1. That's the change I made. So just by calculating this integral, you'll get x2 minus x1. That is, you will get the width of this curve. But notice the width is what comes out of the calculation, not x2 or x1 specifically. Okay. If the potential happens to be symmetric, then of course x2 and x1 are negatives of each other. And x2 minus x1 is just twice x2. So you just divide that earlier result by 2 and you get this result. So for a symmetric potential, you can uniquely find the potential out because you can find x of v out and then solve it for v. Okay. But there are, other than that, many other solutions. Okay, so if you have isochronicity, that is T of E is independent of E, just T0, then x2v minus x1 we just works out with this, the T0 simply comes out of the integral. This integral is trivial. Again, class 12 stuff. Calculate this, you get this result for the width. And for a symmetric potential, this is x2 and minus x1 is just double of x2. So you get this, and that gives you a very well-known result that v of x is proportional to x squared. Okay, so isochronous potential, symmetric isochronous potentials have to be sigma harmonic. Have to be this half kx square form. Okay. However, while the symmetric isochronous potential is unique, There are infinitely many possibilities here if you do relax this symmetry argument, because all you get is the width, right? So just to illustrate, the parabola in red here is the harmonic oscillator potential. But you can have a potential which is a straight line on this direction and a rather complicated curve on this, which ensures that the width is between the two ends of the red curve and the two ends of the blue curve are one and the same. Say, the red and the blue are same width. Okay, at this particular energy, at a higher energy, again, red and blue are the same width. And this potential has exactly the same isochronicity property as a simple harmonic one. Okay. There are actually infinitely many possible possibilities because you can put in any arbitrary curve you want on this side and try to get the width right, and you're going to get an isochronous potential. It is one isochronous potential which is rather easy to even work out without any of these advanced stuff. It's simply this. We had a double-headed kind of spring, which has a given stiffness when it expands and a different stiffness when it contracts. So for positive x, it has some spin constant. For negative x, it has different spin constant. It's very easy to figure out from elementary physics. You don't even need to do all of this stuff here to figure out that this will be isochronous with a time period given by 2 pi by omega, where omega is the harmonic mean of omega 1 and omega 2. And actually, this means the time period is actually the mean of T1, T2. And that's something which is, this result is, of course, very, very straightforward, and it's easy to prove using elementary physics why this should be the case. And notice that all these potentials, the blue curves, all of them are isochronous. They have exactly the same time period as this parabola, the harmonic oscillator potential. Okay. Now, okay, I have 15 minutes, right? Or 20 minutes.
Actually, another question.
Yeah. Yeah. Oh, that's X square. Sorry, that's a typo. Thank you. That should be. Is a okay. I should definitely correct that. I didn't spot that. That one error that I didn't spot is the X squares. These are basically spins. Okay, with a different spin constant when it's expanding as well as opposed to when it's contracting. Okay. Now we have had this foray into harmonic oscillators and not so harmonic oscillators. And now we are going to go back to our pendulum and let's look at the isochronicity issue, the time period. By the way, how big should the amplitude of oscillation of a pendulum be so that you can actually use 2 pi root over L by G as an exact formula?
So less than 4 degrees.
Okay. Why 4 degrees?
Small.
No, but 4 degrees is small, I agree, but so is 5, so is 10.
It is only given in books.
Hmm?
It is given in books.
Well, that's a good point. Because it's given in a book, usually. Okay. Sine 4 degrees nearly equals 1 is of course absurd. What you meant was sine 4 degrees, not 4 degrees, but sine 4 degrees in radians is nearly equal to 4 into pi by 1/8. But exactly, it's exactly correct only for theta equals 0. Sine theta equals theta is exactly correct only for theta equals 0. Otherwise, it's not. Right? Okay. So when you say sine theta is approximately theta, 4 degrees is actually used very often. Basically, because this sine theta approximately equal theta relationship is correct to within 1% at theta equals 4 degrees. 4 degrees is the limit where sine theta is within 1% of theta. Of course, theta in radians, not in degrees. So nobody is claiming sine 4 degrees is 4, right? But 4 into pi by 180 within 1% of that. But we will see whether that's actually a reasonable thing to use. Okay, for the simple pendulum, let's go back to our formula. That is, V is given by this. Energy, of course, is minus mgl cos theta 0, where theta 0 is the amplitude of the oscillation. Right? And so our formula for the time period, just the formula we have been using so far, is an integral from minus theta 0 to plus theta 0 of, this is square root of E minus V in the denominator, And because we are talking of theta here, what should go in place of m is ml square. You have this root over 2m in the formula, now you have root over 2ml square. Other than that, everything is, this is just energy conservation turned around on its head. So this is an integral that we need to do to find out the time period. Okay? And this is not an elementary integral. So unlike the situation which you had for a harmonic oscillator, where the integral was really a sine inverse, but a standard elementary integral, this one is not. This one actually can be rewritten slightly using the fact that cosine theta is 1 minus twice sine square theta by 2. And this will become something like this. Or using the fact that this is an even function and just change it a bit. But if you have this form, the next step is to actually write sine theta by 2 here as k times sine z. That will give you this formula, which is closer to what you would think you can handle. If you do this, this is the final value for the time period formula. This is just a standard symbol substitution. Now, this integral happens to be, well, not an elementary integral, but a rather well-known one. This is actually called the complete elliptic integral of the first kind. Okay, this f of k comma pi by 2, that's nothing but a fancy name for this particular integral. Okay. The reason why these are called elliptic integrals is that integrals of this kind first arose in mathematics when you try to solve a very simple problem. What is the perimeter of an ellipse? Okay. Unlike the case for a circle, the perimeter for an ellipse is actually not a very simple integral to work out. And it works out not, it is not exactly this integral, but a related integral to this one. And elliptic integrals happen to be very important in physics and mathematics. Now, having said that, if you don't know what an elliptic integral behaves like, this is really of no use. This is just a statement. It doesn't help you to figure out what this is going to be like. But note that k is sine theta 0 by 2, right? That's the k that we have here, the sine of that half amplitude. So that's less than 1. K sine z, of course, is less than 1. As a result, one obvious thing that you could do is expand this square root, or not really square root, 1 over square root out in a binomial series and integrate term by term. So this is what 1 by root over 1 minus k square sine square z is. This is just the binomial expansion to the power minus half. And you have minus half, then you have minus half minus 3 by 2 factorial, minus half minus 3 by 2 minus 5 by 2 by 3 factorial, and so on. I would like to point out, for example, if you look at this term, this is 1 into 3 into 5 in the numerator. And in the denominator, you have 2 to the 3 factorial, right? And there are 3 minus 1s, which actually cancel with the 3 minus 1s you get from the minus k square sine square. So this actually is pretty straightforward. The 1 into 3 into 5 into 7, this kind of thing is called double factorial, right? Similar to a factorial, with just terms, integers missing in between. So this is 2n minus 1 double factorial in the numerator, 2 to the n factorial in the numerator. Just take a look at what we had here. For n equals 3, you had 1 into 3 into 5, 2 into 3 minus 1 double factorial, right? This term. Then you have 2 cube, so that's 2 to the n, and n factorial. And this is the integral that you need to. This is what you need to integrate from 0 to pi by 2. Okay. Now, once again, sine to the 2nz, elementary integral which you must have done in your class 12. This is one of those recursion problems that people do all the time. And it so turns out that the integral of sine to the 2nz, when you integrate it from 0 to pi by 2, happens to be exactly the same as this factor in front. Okay, so this is what f of k comma pi by 2, this integral really is. Okay, this, and when you put that back, this is what the formula looks like. I've just replaced k by its original value. It was 2n was there, that's fine. But okay, this is not really that difficult to figure out, because when n is 0, that's a leading term, what you get is just 1. For n equals 1, you get this 1 by 2 whole square. For n equals 2, you get 1 into 3 by 2 into 4 whole square. For n equals 3, you get 1 into 3 into 5 by 2 into 4 into 6 whole square, and so on. So this is a series that you get, and the first term is what you actually call the pendulum formula, T by root over L by G, right? So these are the additional corrections you get because of the finite amplitude. Yeah. And notice that although this is an infinite series, these terms, these factors become smaller and smaller as you go by. Sine theta 0 by 2 is anyway smaller than 1, so that term becomes smaller and smaller when you have higher powers. So typically, very often for small amplitudes, you can ignore all of these terms, you get 2 by root over L by G. And for slightly larger amplitudes, you can't ignore this, you have to keep this in. But let's see what happens if you keep the next term. Or more importantly, instead of sine theta 0, you would want to actually write this in terms of theta 0 itself. So just use sine theta 0 by 2 is theta 0 by 2 minus theta 0 by 2 whole cube by 3 factorial and so on. Plug that in, work it out, and this is the t that you get as a function of theta 0. Okay. This straightforward algebra, you just start here. Instead of sine theta 0 by 2, you just put in this expression, put in the square of that, be a bit careful and collect the powers properly, and you are going to get this form. At least for not too large theta, you notice that this term is going to be pretty small. There's a 3072 in the denominator, right? So this was not too large theta 0. Sorry. The change between t and t0, t0 of course is 2 pi root over L by G. The standard pendulum formula is given by theta 0 square by 16. So the fractional error introduced because of this finite amplitude is given to a very good approximation by this quantity. So now this 4 degree, okay. Well, where did this number come from? We already said that. Sin theta agrees to theta within 1% for angles smaller than 4 degrees. That's where the 4 degree limit comes from. Frankly, I'm not really interested in sin theta being approximately equal to theta. When I'm using this to measure time period or measure G, for example, from the time period, what I'm really not interested in sin theta in this sin theta approximately theta, but in what it predicts for the time period. And note that the fractional error is theta 0 square by 16. So when will the fractional error be 1% in time period? When theta 0 square by 16 is 1 over 100, right? And that means theta 0 square is 16 by 100, 0.16, and therefore theta 0 is 0.4. So the formula, time period formula which you use for the pendulum actually comes close enough to within 1%, which is reasonably close, for an angle as large as 23 degrees, 0.4 radians, not close to 4 degrees at all. Okay? Yeah. However, there is a reason why 4 degrees is still a good idea. Remember, we ignored several things. We ignored air resistance. Large amplitudes would mean large amount of air resistance. So 23 degrees, although the formula tells you that, is not a good idea. Don't make. And the other real reason why 23 degrees is a bad idea is you need to make the pendulum move in a plane and without spinning around. Both of these would, anybody who has done this experiment in the lab would know that that's actually very difficult to do. Okay, especially if your amplitude is large, preventing the pendulum from deviating from a planar motion or going in a twist is very, very difficult. So small amplitude is still good, but not for the sin theta approximately equal to theta reason, but basically because it's easier to control your experiment for small oscillations. Okay. Okay. Give me 10 more minutes. Okay, so the really interesting thing comes now, and so I will not really be able to do justice to that. But let's see. What can we say about the displacement of the pendulum as a function of time? So far we have just talked about time period, but what about its actual motion? Of course, you would expect a deviation from simple harmonic results, but very recently a colleague of mine tried numerical calculations to figure out what the oscillation would be like. Simple solution using pi-pi integrations. And there, he was very surprised because he got something which looks very, very close to simple harmonic. Okay, simple harmonic. It looks like a simple harmonic sinusoidal oscillation, at least for an amplitude of around 1 radian, which is pretty large. Okay, but we can actually understand that pretty easily if you look at. And then you do expect deviations from the simple harmonic result. This is the simple harmonic result, right? Instead of x, I've just used theta. You do expect deviations from that, but how, by how much? That's the question. And now I have a numerical graph here. Notice that at least for one swing, which is here, the two curves, okay, these are two curves. I'm pretty sure you cannot read the legends. Even I can't read the legends here myself. Okay, the pendulum is a blue curve. Okay, and the harmonic oscillator is the orange curve here. And notice that in the first swing, you can hardly distinguish between them, but as time goes by, you can see a big difference. Okay. But the major reason that you see a big difference is primarily the fact that time period of a harmonic oscillator and the time period of the pendulum, that is, time period that I get using 2 pi root over L by G, and the actual time period of the pendulum for an amplitude of 1 are actually quite different. That is why the curves are separating quite a lot. Okay. How do we solve this? Well, we have an expression for d theta as a function of dt, right? We use this to find out the time period, but instead of that, I could just do an integral. So if you just do an integral not from 0 to pi by 2 or 0 to one end to the other, but from an intermediate from over any arbitrary time, you should be able to find out. I think I've got this wrong. This is again a type. dt should be d theta. dt should be here, d theta should be here. Okay. But anyway, the basic idea is this is an integral which can be done, gives rise to an elliptic incomplete elliptic integral of the first kind. I'm just showing off so that you realize that it's really something complicated that we can work with. But instead of doing that, what we will do is we will try perturbation theory. So how many of you have done perturbation theory before? Anybody? Quantum mechanics. Okay. Yeah, but after all, since what is the most common kind of perturbation theory in quantum mechanics? What's it called?
Time independent.
Yeah, but there are many versions, by the way. The one you do is usually called what? It's called Rayleigh-Schrodinger. The Schrodinger is basically to tell you that you are using it for quantum mechanics, but the name Rayleigh should tell you that this was really around long before quantum mechanics came in. Okay, so classical theory, in fact, perturbation theory was used in classical mechanics for a long, long time to study motion of the planets around the sun, all kinds of situations. This one actually, the pendulum happens to be a rather difficult thing to study using perturbation theory, surprisingly. So let's see. Okay, what we will do is we will throw away all these concepts, L by G and so on. I will just use units in which L by G is 1. And always do that. By the way, in advanced physics, we keep on throwing away units like crazy because we can change units so that many of these constants just become 1. So here we do that, and just to show that we are using different units, I'm going to call theta x. So the equation simply becomes this. Okay. Now, even if x is large but not too large, I can write sin x as this. Approximating sin x by x was the harmonic oscillator approximation. There's the next step. Okay. So what we can do is solve this problem, which is a cubic approximation to the pendulum. And is that a good approximation? The answer is actually yes. Here I have just shown you the pendulum, which is the blue curve. I think you can't even see the blue curve, or you can, just about here. The blue and the orange curve really match quite well. Okay. One is both of these are numerical solutions done using standard Python integration programs. And basically, you can see that the two curves come very close to each other. So if you're approximating the pendulum with a cubic, it's much better than approximating just dropping the x cubed term, right? Okay. So now this can be written down in the perturbative form like this. You can write x double dot plus x, which is something we know and love. We can solve this pretty easily. Equals epsilon times x cubed. This term I've just moved to the other side. And epsilon here is of course 1 over 6. And I'm going to leave this as it is because I'm going to use this as my perturbation parameter. Now, for those of you who have not done perturbation theory before, how does it work? You just, of course, you know that x has to depend on epsilon, right? So what you do is you assume a form for x. That is, x is some function of t. So write that as x0 of t plus epsilon times x1 of t plus epsilon square times x2 of t plus epsilon cube times x3 of t. And so instead of a simple but non-linear, okay, not simple, but a single non-linear equation to solve, you now have infinitely many things to worry about. You have to find out x0, x1, x2, x3, and so on. So if you really have to worry about infinitely many things, why is this at all useful? Basically because first of all, it is easy to calculate x0, x1, x2, at least easier to calculate x0, x1, x2. And secondly, because epsilon being small, in this case is 1/6, higher powers are going to be much smaller. You can drop the higher powers. So you can, instead of worrying about infinitely many terms, you can worry about a finite number of terms. So now, how does this work? Well, this is your equation. This is your x. Now, plug this in. The left-hand side is very straightforward. You just take double derivatives of all the x's on this term, and this is just the x. The right-hand side takes a bit more care. You have epsilon, and then you have this thing whole cubed, right? But now, if you were to collect our like powers of epsilon together, say epsilon to the 0, what is epsilon to the 0 on the left-hand side? X0 double dot plus x0. What's epsilon to the 0 on the right-hand side? 0. There is no, every term here has epsilon, right? Okay. So epsilon x0. That's the lowest order. Epsilon x0 cube, that's the lowest order term. Okay. So first order, 0th order x0 double dot plus x0 on the left, 0 on the right. First order x1 double dot plus x1 on the left, just epsilon x0 cube on the right, and so on. The only tricky part is expanding this out in powers. And note that because I've written left-hand side up to epsilon square, the good thing to do would be to write the right-hand side also up to epsilon square. And that's pretty straightforward. Actually, that's just this. It's just the binomial theorem for power 3 used here. Okay. Remember, this is the quadratic term in epsilon because you already have an epsilon outside. So now compare, you get equations. And you can keep on writing down equations. What's great about these equations is these equations are much, much simpler. The first one is, of course, standard harmonic oscillator equation. The second one is much simpler than what we had. Why? We had this, right? The second one, third one, my claim is all of these equations are much, much simpler than this one.
Because I can manage to calculate x0, you will get all the right hand sides.
Yeah, the point is what makes this equation difficult is that it's a non-linear equation of an x cube. All of these are actually linear inhomogeneous equations. You have complicated looking things on the right, but all of these have been calculated in the previous step. Say when you get to x2, on the right you have x0 square and x1, which you have calculated before. So you know the right hand side completely. So these are just driven harmonic oscillators, right? So quickly, initial conditions. Well, basically, let's do a very simple initial condition, a and 0. If you do that, well, the 0th order equation will simply be this with these initial conditions. You know what the solution is, right? A cos t. So what about the first order equation? That's the first order equation. Now you know x0 is a cos t. Plug it in. So you get a standard driven harmonic oscillator equation with cos cube q on the right hand side. That's actually pretty easy. You know how to handle sines and cosines in a harmonic oscillator driving term. Elementary trigonometry. And therefore, I'm pretty sure all of you know this, right? This equation has a solution which is the solution of the corresponding homogeneous equation, b cos t plus c sin t, plus a particular integral which you get by using the 1 by d square plus 1 operator. So can anybody spot a problem with this? Not with this, but in the next step. How do you calculate this 1 by d square plus 1 acting on cosine omega t? Well, there's a simpler way. For cosines. Actually, the binomial would actually give an infinite series. Can it still be done? Well, not 3 square plus 1, it's minus 3 square plus 1. D with I omega. That's a replacement that works. Again, class, you did this, all this in class 12. Maybe you've forgotten by now. Trouble is the term in blue, cosine t, will give a vanishing denominator. Minus 1 whole square, minus 1 square plus 1. Of course, that doesn't mean that this really gives you infinity. It gives you a slightly more complicated term. It actually gives you a t sine t kind of term. The details of this calculation is very straightforward. You can all do it yourself. But the important thing is, ultimately, when you put in the initial conditions and everything, you end up with this additional piece. This is called a secular term, a term which keeps on growing in amplitude. Okay, and why is it there? Because there is a oscillation. There is a term, driving term on the right hand side, which is of the same frequency as a natural frequency. Remember, this is an undamped harmonic oscillator. An undamped harmonic oscillator, if you try to drive with a term which has the same frequency, you're going to get a growing solution. And that's exactly what's coming out here. So let's see, is this any good? This is an approximation that we have. So this is after you put in epsilon equals 1/6. Remember, this is x0, that's epsilon times x1. Once you put in epsilon equals 1/6 and calculate, this is what you get. In fact, this region, if you could really see it clearly, is actually better than before. But this region is much, much worse. Notice that the t sine t is actually growing with time. So you're getting a solution which definitely will be worse and worse as time increases. Unlike the pendulum, which has an oscillation of a particular amplitude, this keeps on growing in amplitude. And in fact, because this term t sine t is there in x1, the magnitude of x1 is going to exceed, even epsilon times x1 is going to exceed x0 if you wait long enough, right? X0 is an oscillatory thing which goes between plus minus a, but x1 is a term which keeps on growing with time. So what happens is this basic idea of perturbation theory that all of these can be calculated order by order, and the higher order terms are smaller than the lower order terms, that drastically breaks down here. So regular perturbation theory will break down. Now, I don't have the time at all. I've already overshot this, but I wanted to end with the improved method, which is actually Poincare. It's called a Poincare-Lindstedt perturbation, as opposed to regular perturbation. I'm just going to tell you the basic idea. The basic idea is simple. Here the trouble is you have the secular term, the term which keeps on growing with time. Now, everything else has a period 2 pi here, but the pendulum does not have period 2 pi. Right? The pendulum's time period actually depends on omega, on the amplitude. Remember, this is an omega equal to 1 pendulum. It would have 2 pi time period for small oscillations, but for large oscillations, it doesn't have that time. So the trouble is, this particular perturbation theory fails basically because it fails to capture this fact that the amplitude also has changed. Now, you have to correct for this. And the way you correct for this is simple. Instead of using t, you use tau, which is omega t, where this omega, the new parameter, which is capturing the fact that the frequency of oscillation has changed when amplitude has changed. So this is, once you do the substitution, it's straightforward. The d2 dt2 becomes omega square d2 d tau. Okay, everything else stays the same. But now when you do a perturbation, what you're going to do is you're going to assume not only is x a function of epsilon, but omega, the frequency, also depends on the perturbation. So it also depends on epsilon. In other words, assume both. And now, okay, the algebra is pretty straightforward. I'm pretty sure all of you can work it out. So let's not go too much into that. But now you get a bunch of equations where, because of these extra terms on the left-hand side, you get, and when you move them to the other side, you get correcting terms. Now, how does that help? Well, let me just show you one. The first order equation, zeroth order equation is again the same as before. Okay. X is still a cos tau, no changes, except that it's a cos tau now, not a cos t. So there's time period of 2 pi in tau, but time period of 2 pi omega in t. Okay. But what about x1 equation? X1 equation looks much more complicated. It was like 0 cube only now, before. Now it has this. How does it help? Okay, by the way, the double dot here are derivatives with respect to tau. I've changed the notation a bit here. But now note that this is what you have. What was the term that really was giving you problem before? The cos tau, right? Because that was a term which gave rise to this tau sin tau as a result. Now, how can you manage to get rid of that? Remember K1, the perturbation term which changes the omega is in your hands. Notice there are two cos tau terms. You just choose K1 such that the cos tau terms vanish. Okay. So this secular term, the term which causes growing amplitude, that goes away. This K1 was doing this. And then the rest of the calculations are actually simpler because the secular term goes away. You're just left with this term and your integration is trivial. Okay. What is important is that now you're taking into account the fact that the time period actually changes. Now, this method can be used not only here, but for other things, like, say, if you have something called a van der Pol oscillator, which has things called limit cycles in nonlinear motion. All of those things can be easily understood by using this kind of perturbation theory. So this is a very broad method. I've just indicated this using a simple example. So just this is consistent with whatever we have done before, but let me just show you. This is the pendulum curve and the perturbation curve. You can hardly make out the difference at all at this scale. Okay, you should really plot the difference to see. And here you see, remember, okay, this looks like a pretty large amplitude oscillation in the first order. That's the first order perturbation correction. But notice my motion has an amplitude of 1. This oscillation is an amplitude of 0.02. So even in the first order, your calculation is correct to within 2%. And the second order is much, much better, as you can see. And you can keep on improving upon this. Okay, so to land up, to finish this, what we didn't cover? We didn't cover the theory of the tautochron. We didn't cover the wonderful idea about parametric resonance, which tells you why a swing, children's swing actually swings more if you can pump up and down your legs at the right time. The mathematics behind it is actually surprisingly complicated. The elastic pendulum happens to be something which shows parametric resonance of the kind before, also shows a lot of other behavior. You can have an inverted pendulum if you shake the pendulum point of suspension rapidly enough. The pendulum will actually oscillate about the upward vertical, so-called Kapitza pendulum. If you have a driven damped pendulum, you can have all kinds of chaotic behavior. So if you want to study chaos and nonlinear behavior, and the basic mathematics behind that, the kind of mathematics that we did just a while ago, that will tell you what this is. Well, the double pendulum is just a pendulum stuck to another one. This is a picture where the lower pendulum had an LED stuck to it, and you have taken a time-lapse picture of the motion. And this is basically the upper circle. Basically, is the LED stuck to the upper pendulum. After all, that's just stuck to a single point, so it goes round in circles. But the other pendulum does this crazy stuff. This is basically chaotic behavior. You can study all kinds of chaotic properties here. And of course, I didn't talk about the Foucault pendulum at all, which is a very fascinating topic in itself, and many, many other things. Okay, so where can you read more about it? I would definitely suggest reading this book. And by the way, the time period calculation that I gave you, the potential from time period calculation, that's from Landau-Lifshitz mechanics. This is a very fascinating book about the history of the Foucault pendulum and how it was used to actually convince a lot of people that the Earth really rotates. And these are more technical books, but they are also very interesting and important. Many of these stuff that we didn't cover, they're covered there. I think I've way overshot my time and okay. The final slide is very important, so that has to be shown. So we are running short of time. Let us go to